syllabus. Okay, anybody? Online, offline, Zarar is there, okay. Zarar, Vanish, Rabi, okay. Anybody guys, I can just do a quick recap of whatever we learned during the last 2 days. Last 2 Saturdays, I mean. Sorry? So firstly, we began with some of the concepts of marketing, right? At a very high level, NPS score, right? NPS score, OSAT, CSAT, just remember that. Who's a detractor, who's a passive, who's a promoter, remember that part. Brand funnel, different stages of brand funnel. That is something which you need to remember. Third one is the 4 P's of marketing, right? That is mainly used for marketing mix models and such things. Then the first day, mainly the emphasis was on neural network, which is 3 points about neural network very quickly. MLP, multi-layer perceptron. The more important thing is that neural network is mainly used for non-linear, mostly for non-linear data models and such things. Okay, gradient descent algorithm is something which you need to keep in mind. Okay, then we looked at the accuracy, train test, those sort of things we looked at, and I think we paid some attention to precision, recall, F1 scores, all that, right? Day 2, choice models, right? Long data, white data. What's the difference between long data and white data? And then Manjunath is not there. He's not well, is it? Any problem? Okay. He might join, which means he'll not join. Okay. Okay. Let's come back to this, please. After this, what did we do, guys? A utility function, right? Some product multiplied by the coefficients will give me the utility function. That utility function, how to convert to market share we saw, right? Simulate and then obtain the prediction. How to compare to multinomial logistic regression models. That's also something which we saw. Interaction effect, intercept term, suppressing the intercept term. How do we compare to choice models? That is something which we saw. Okay. So today we are in day 3, right? Some important ideas we will discuss, mostly about second generation machine learning models. We'll see what are these second generation machine learning models. My agenda for today would be within the first half. I just want to give you some idea of bagging technique, and then the second half mostly move on to a priori algorithm or market basket analysis. So today we'll be talking about what is called as meta models. Okay. Meta models in a typical scenario is we all are familiar, right? If you have to build any classification model, what do you do? From top left to bottom right, you will just trace the sequence, right? When I say from top left to bottom right, you'll trace the sequence. How do you do? You get the base data, you check the data quality and such things. Then you split the data into training and testing, run a model in the training data, right? Score the test data, cross validation on examine the result with respect to the test data, and then basically we check, right, the accuracy and look at some of the model diagnostics, correct? Now this is what you do, right? Now do you notice any can you identify when you have built any model, have you been able to identify a couple of problems when you take this route? You built many models, right? You built so many models so far. Have you basically found yourself in a situation wherein there are certain models which were like slightly dicey, you're not very confident about the results, final results and such things? Imbalance, that's a specific problem, right? Let's say you've beaten all these things, right? You run the model, you've got the accuracy also, right? Now at this stage, have you found the model results less than assuring, right? I'm not so comfortable, the model results look very, very dicey. Have you ever found that? Yes, no? When? Where?
In my case, at this because of one is
which we were discussing together, yeah. Right? Yeah. Right.
Data points were not enough.
Data points were not enough. Okay.
Couple of machines had quite a large number of data points, but some other machines like kind of 1 or 2 data points.
Okay.
So that was the only issue. So when we had the overall prediction,
right,
and also the kind of attributes, like we had high cardinality features. So that is also another issue. Like even if you're trying to group them, it was not able to group properly because each had its own behaviors.
Okay, separate behavior. Okay. So here, right, when you go through this sequence, let's say you have training and testing, correct? Typically, in any machine learning or statistical model, there are two main challenges that you'll always encounter, right? One is what is called as the problem of overfitting, correct? What do I mean when I say overfitting? There's a huge gap between the training and the test, right? In training, maybe I've got 92% and the test, maybe I've got 62%. So that's a typical problem of overfitting, correct? And the second one is basically low accuracy. The overall percentage of accuracy itself is, let's say, 50%, 55%, and I do not have sufficient confidence to take it to my client, right? 55% accuracy, obviously, I'll not be able to take it to my client. So these are the two challenges that you will always come across when you build any machine learning model, deep learning model, AI model, statistical model, any model that you build. Lack of accuracy, this is problem number one. Lack of accuracy, right? So, and the second one is basically a lack of robustness. The model is not basically robust to a different data set. The moment you change the data set or sample slightly, the accuracy, whatever you obtained, collapses, right? So first is lack of accuracy, right? Second one is highly accurate model on the train, but testing, it reduces. So this is lack of robustness and lack of accuracy. So these are the two main challenges that we will be sort of solving. Now, any idea how do we sort of solve this? Okay. Okay.
Hello.
So that the model has the similar accuracy level for training and testing.
Okay.
And then also when we are training, basically what we have found is like train only on training data, right? There's training data, but also in the sample size based on cross validation, so that it also rules and does the test.
Okay. Okay. So we'll mainly be talking as to how we can tackle these two problems. Right? How we can tackle these two problems. Okay. And I'll just give you a 10,000 feet perspective, right? If we have to get down to the nitty-gritties of this will take a long time, right? So this is what I'm summarizing, guys. The one common problem that you'll always see is low accuracy. Inaccurate models, and no matter, let's say you change your hyperparameters also, it is not able to do a lot of justice. It's not able to pull up. Maybe 1%, 2% max to max accuracy will be able to boost up, right? The second problem that you may see here is lack of robustness or generalizability, right? So this problem, when the model is not very robust, it is called as lack of generalizability. So low accuracy and generalizability, these are the two main challenges in any machine learning problem, right? Now we'll be seeing as to how we can tackle these two problems. Now I've gone beyond hyperparameter tuning, right? Many times you can tune the hyperparameter and such things, it will produce some results. But even if that does not work, what else works, right? So to answer this, right, we'll be talking about what are called as meta models, right? It's a school of thought rather than one single model. It's not like a logistic regression model or something. This entire school of thought is what is called as meta models. Now, when we learned machine learning and such things, data mining in our school days, sorry, not in our school days, but in our college days, we didn't have this concept, right? Mostly decision tree, a bit of segmentation, time series, this is what we were taught, right? But the problems of first generation machine learning models, your decision tree, your segmentation, linear regression, logistic regression, all these are first generation machine learning models. They had their challenges, but only in the last 10, 15 years, basically, they've been able to address the challenges of the first generation machine learning models through meta models. Now, there's no guarantee that it will work always, but the school of thought is designed in such a way that it works. Usually 70 out of 100 times you can expect better results with meta models. Okay, is the problem statement clear? Low accuracy and lack of robustness. We're just now starting. Okay, so here in meta models, what we do is basically the first three steps will remain the same, right? Split the data, right? Data cleaning, everything by and large will remain the same. But here, how do we solve the problem of generalizability and robustness, right? So what a simple school of thought here is more the better. Instead of running one model, run two. Instead of running two, run three. Instead of running three, run four. When you run multiple models, basically, you run multiple models and combine the results of multiple models, and then you score, and then you check the accuracy. So you can either run same models or you can run different class of models. Both these options are available to you. Right? Let's say I want to run 10 decision trees, you can run that. Or let us say I want to run one decision tree, one support vector machine, one logistic regression model, and then stitch the performance of these two things together, then it works. The simple idea here is that combined models tend to outperform tend to address the challenges of single models. Right? When you're running a logistic regression model, there might be a pattern which it has missed out, correct? Or there might be a signal in the data, there might be a pattern in the data which it has sort of which it has failed to detect. Now, when I run multiple models, the idea is basically that it is able to pick up the second model picks up the pattern which is undetected by the first one. The third model picks up the pattern which is undetected in the first two models. The fourth model picks up the pattern which is undetected in the first three models, so on and so forth. How many models should you run? That depends upon the capacity of your desktop. There is no upper limit. Some people say 100, some people run 500 trees, some people run 5,000 trees and such things, right? Is it clear? Right?
Same way, ensemble.
It's more or less like your ensemble technique itself.
So it's voting.
Voting is one of the things that we do here.
Yeah.
Eventually. Sixty 20, you try it, you usually does not work in a big way. If it works well and good, you don't have to come to this, right? I'm talking about a situation wherein you have tried all these things. You have done your hyperparameter tuning from 80s 20, you have, let's say, changed to 75 25. If all those things work for you, fantastic. You don't have to come to this set of techniques at all. I'm saying that there are many complex problems which cannot be addressed purely by hyperparameter tuning. Then what? Then basically, this is the one set of models which usually do well. Okay.
Guidance that okay, my perception says that the result what we got is correct.
See, we never go by perception actually, right?
You said right starting with report results. You feel that you are not satisfied with the results.
Yeah, let's say.
But the other way,
Yeah.
I am satisfied with my result, but
The management is
not exactly management. But the thing what it has done behind itself is wrong.
So the model
It needs more refinement or something.
the model needs more refinement. Or one is, see, there could be two challenges. One is the problem with the data. You have not done data pre-processing well. Second one is because of the wrong choice of the model. One is the wrong selection of the model. Second one is basically a wrong pre-processing of the data, or you might not have paid sufficient attention to pre-processing of the data. Data pre-processing and such things, if you have done adequately, usually you will not run into low accuracy and such problems. Data pre-processing, if you have done everything properly, usually you will be getting a decent level of accuracy and such things. Second one is basically the wrong selection of the model. Now that becomes a bit of a problem, because if you're using a linear model where nonlinear patterns are there or vice versa, then again your accuracy and such things will suffer a bit. So for both these problems, you can use some of these techniques which we are talking about. Okay. So combined results will always work better than yes.
See, when you say that run a multiple model,
Yes.
the question is that there anything of a series of a way that you try this and next you try this, so that it can able to identify the missed variable or missed result, and it can work on that.
second thing, if the training, if the, when you say that first model can miss a one, something you mentioned, what is that?
Patterns.
Patterns. The first model, if it is missing a first pattern, the second model is going to identify, and third model, it can going to identify the previous, pattern missed by the previous models. In that case, is the train and test data the same, and why the
Train and test will be the
different
same.
models can miss the patterns?
Different models will not miss the patterns. That is the idea behind running different models. So your first question, let me answer that. Your first question was basically, what is the first question? I forgot.
Is there any series, like when you say that?
Is there any step by step? Okay.
Yeah,
Is there any step by step? Okay, I got. Let me address the first. Sorry, again forgot. Sorry. No, not one. The question, please.
Is there a series?
Is there a step by step? Is there a series? Okay. Is there a series?
Let's take for example,
Similar.
we do logistic regression. After logistic regression.
What should I do? Okay.
Yeah.
Okay.
Let me clear my thought, like,
Okay,
it's
okay.
like there is a basic model, let's say that a linear regression model. It's very basic. You can say that it's very basic and it can able to handle these things. That is the reason it can miss. Then you go to SVM. Then you go to decision tree or something.
I understood.
So that's.
I got it. Yeah.
Because training and test data will be the same.
Training and testing, we are not, training and testing has got very little to do with the overall accuracy and system, very little, right? Now, in terms of what is a step-by-step procedure, ideally start with first generation machine learning models. Start with, let's say, if you're dealing with a classification problem, your first step should be to try with a logistic regression model. That's the first thing. Now, if you run a logistic regression model and you get sufficient results, the matter ends there. Question is, you don't get sufficient, you do not get adequate results. Then basically you have another set of models which are called as non-linear models. There you can try your, as a second step after logistic regression model, you're not satisfied with the first set of models. You can always experiment with your SVM, support vector machine models, or you can experiment with your decision tree. Third one is your neural network, right? All these are basically good at handling non-linear set of models. Let us say this also does not work. Then get into hyperparameter tuning of these models, right? So this is all part of the second set of activities that you do. Let's say in the second set of activities also you've done something, you've got decent results, but not very satisfactory results, not very highly accurate models. And the third set of steps that you need to do is what we are going to talk about, meta models. Yeah.
See, if the data is a linear model, then
Yes.
you suggested us to use the first generation regression models. If the data is linear model, then we have to skip the non-linear models because
Yes.
it will
There's no point,
cause
right?
that.
Yes. Okay. So we are going to run multiple models and combine the performance. That is the central idea behind this set of models, which are called as meta models, right? So two effects in any machine learning model that we are worried about, that you will be always worried about. One is what is called as bias, right? There's a word which you will hear. One is bias, and the second one is basically variance, right? Now, why do we get bias? Error due to model choice. The choice of the model that you have made is wrong, and therefore that results in bias. Okay, so can our model better represent the true best predictors, correct? So gender is a best predictor, but my model has given 7th priority to it. So if gender is the best predictor, but if it is going in the 7th predictor, obviously it's like, if I have a good, let's say, I'm just giving a very crude example here. Let's say I'm making a movie, but the best actor could be Amitabh Bachchan, but his role is cut short to only 20 minutes. Right, you can imagine the fate in the box office, right? So all the key drivers have been given 7th position, 8th position, 9th position, which will reflect in high bias. And third one is gets better with more complexity. Gets better. In fact, the bias basically gets worse and worse with more complexity. That's what I'm trying to say. Next one is basically variance, and this could arise because of randomness due to data size. right? You have taken a very, very small sample size and such things, and therefore that can lead to high variability. This one gets better with more data, worse with more complexity. When we say variance here, what we mean is basically training, I'm getting 90. If I take first sample, I may get 65. Second sample, that is a test, I may get 50, 52. So there is so much of fluctuation, right? This is again a model which cannot be trusted. So what is the solution to beat variability? Improve the sample size. It gets better with more data, and it gets worse with more complexity. When I say complexity, I'm referring to dimensions. As the dimensions increase, this guy gets worse. That's what we say. Right? Bias and variance. So here, when I say gets better with more complexity, adding variables will help. Right? So which one to minimize, which one to maximize, this is always a question mark, because we have to do some trade-off. You can't always have best of both the worlds, right? We'll try our best to have best of both the worlds, but usually we may not always succeed, right? So one problem that we are trying to address is bias. The second one is the problem of variance. Yes.
Just can you explain me how the one important variable can be, given the seventh position or least position? I was not getting the idea.
Say, for example, you're running a logistic regression model. Logistic regression model, the performance of logistic regression model is heavily, let's say, influenced by salary. Logistic regression model has told that salary is the most important predictor, right? Now, if you run some other model, right, salary may be in the seventh position. Salary might not be the top driver of your performance. It is not salary, it is some other model. How do I?
How do you identify?
So when you run multiple models, you can see here the top three predictors will basically will not be in the same position. Here, salary is the first position. The second model, it is the 10th position. If you run a SVM, it may be in the 5th position. So it means that there is so much of inconsistency that the entire performance of the model is driven by different predictors. So these predictors are not consistently emerging as important variables.
So whenever we actually recently we have tested some of the data, right? So whenever we run the model, it will give the values. So in the series, so in that series, you count it like from the top to down.
Identify, look at the top three drivers. That's it.
Yeah.
Top three drivers you see. Top three or top five drivers. If it is consistent, your model will usually basically not give you the problem of overfitting will not be there. If the top 3 or 4 drivers are inconsistent, that's when basically high bias will come.
Can be related to the progress statements also. And I'm trying to prove the progress statement on a gender, but it is not considering gender is itself as in a
yes,
private.
yes, because for each of these models, the underlying formula is different. Okay, bias and variability, these are the two problems that we are trying to address. Okay, so far we are clear. Okay, so I just put up this slide to just make you familiar with these terminologies. You'll always hear these things, these words, basically overfitting, underfitting, and good balance. Overfitting is basically every pattern, it becomes so rigid, right? That it is, you can see the red line here, it has almost faced the smallest of the patterns. And the test data is the same pattern, geometrical shape is not there. Obviously, you'll have huge, you'll have a lot of inconsistency in the results. High bias is this one straight line. You can see here it is not at all considering these blue points which are above, below, as well as here. So this is what I mean when we say high bias. This is what leads to high variance. And a good model, which we should always aim to, right? Any machine learning, deep learning model should be something like this, which has low bias and low variance. We may be somewhere here, we may be in this trap, or we may be in this trap when we build a model, right? From this trap and from this trap, we are trying to move towards this area where we have low bias as well as low variance. Geometrical, right? Reduce high bias, right? So some strategies here. Let's just quickly look into this. So predictive error, model complexity means what? Add more variables. It becomes very, very complex, correct? So on the one hand, we have model complexity. And the other hand, you have basically predictive error, right? So high bias, as you build a very, very complex model, right? It will lead to high bias, right? So to tackle the problem of bias, what we do is basically we use a technique which is called as boosting, right? The first set of techniques that we will be using is called as boosting techniques. first set of techniques. Now, boosting will solve the problem of bias. Okay. And the second set of techniques that we are interested, second set of problems which we are interested in solving high variability would be basically bagging. So under meta models, basically, we are talking about two schools of thought. One is what is called as boosting. Second one is what is called as bagging. Boosting is the medicine for bias, right? A bagging is the medicine for your what? High variance. So if you have a lot of variables or high dimensional data, right? Let's say 30, 40 variables, and I'm not able to make up my mind. I am not able to decide out of these 30, 40, which are the most important, right? The moment you have 30, 40, rest assured that it will lead to high variance, correct? If you have shortage of data, it will lead to high bias. Fewer predictors will lead to high bias. A lot of variables will lead to high variance, correct? Right? It becomes a very complex model, right? Now, these sort of models that we are talking about, mainly these challenges mainly arise when you're working with decision tree, right? Decision tree, you have the parent node, right? You have the leaf node, right? Sorry, parent node, and then you have what is that called? The child node, sorry, yeah. First level, second level, and third level, right? But imagine if you have 30, 40 variables, you may have a very deep tree. You may go on to 7 or 8. 7 or 8, definitely accuracy will be very high in that case. But it will lead to overfitting. Most of this decision tree, basically, they're interpretable, very simple, but leads to overfitting problem. And therefore, to mainly address the challenge of overfitting, these set of models have come into existence, boosting and bagging, right? I'll just explain this. Boosting and bagging, very important, because even if you look at some of these competitions and such things, Kaggle competition, that competition, this competition, a lot of boosting techniques are used widely. Okay. Okay. So I'm just summarizing here, guys. What do you do? What do you do for each of these problems? When you have low accuracy, straight away you go for boosting, and when you have the problem of robustness or generalizability, use bagging. This is a very simple one-slide solution for what we are having. Within boosting, how does it solve the problem? We'll just talk about it. And within bagging, right? How do we solve the problems? Let me just talk about. First set of techniques, mainly boosting. Let's talk about boosting. Correct. So what happens is basically there are 5 steps that I've listed here, right? Within boosting, it's a class of models. It is not one model. It's not one single model. There are at least 4 different options of this. First one is what is called as AdaBoost, right? It's the most basic or the prototype of boosting technique. Second one is what is called as GBM or gradient boosting method. Third one is what is called as XGBoost. XGBoost is the one which is popularly used for all these competitions. And you can see many of these winners usually use XGBoost model. And the last one is what is called as light GBM. Light GBM. These are the 3 or 4. These are the 4 boosting techniques. Extreme gradient boosting. It's a flavor as SG boost, stochastic gradient boosting. You can use that also. Okay. Right. If I have to just explain step by step how this works at the backend, right? We don't have to manually do it. Today we have codes and such things. So all these things will just happen in one step, right? C5.0, right? It's a decision tree model, right? C5.0 is a decision tree model, right? That is built the usual way. I'm just taking the example of C5.0. It can be for any classification. It can also be for any regression kind of a problem. This is your first model, correct? Now, when we are building the model 2, what happens is that the second model is built in such a way that it focuses on records that were misclassified in the first step. Your C5.0, maybe it has got 60% right, correct? That's the first model. Now, the second model, what we are doing is the balance 40% of the records which are misclassified in the first model, that is given higher weightage as far as selecting those models, selecting those records occurs. So you select those records and you use the second model to train and learn the patterns which were misclassified in the first model using the second. I built the first model. Yeah. Let's say I've got 60%. That's the accuracy. What happened to the 40% that was misclassified? Now I'm going to build one more model, which tries to learn the pattern of the balance 40% of the cases which were misclassified in the early stage.
Then are you taking the predicted data? Because the predicted data will be everything.
I'm taking the raw data. Models are always built in the raw data, right? So I'm just taking the raw data here. Imagine that I've got 100 records, correct? I've built a chain model. I've got 60% accuracy. 60% accuracy means what? 60% of the times I've made the correct classification.
Yeah, correct.
Balance 40% have been misclassified. Correct? So what does this mean? My first model has failed to learn the patterns of these 40% of the people. Got it?
Yeah.
These 40% of the people are given higher weightage when I build the second model. So when I build the second model, my second model is designed in such a way, is built in such a way that it learns to classify these balance 40% of the records properly.
Is there a technique that you only take those 40?
Yeah, that's why we are saying, right? So the second model is built in such a way that it focuses. Its emphasis is on those records that were misclassified. It is mainly focused to design it is mainly focused to handle those set of records which misclassified in the first set. Okay. Now, what about the third one? Let us say this model is built to focus on the second model. So out of these 40 records, let's say there is a very complex pattern. The second model has successfully been able to understand 20 records. Correct? Right? Balance 20, it has also not been able to do. So the third model is designed to address the challenges of those leftover records of 20. Right? Like this, you keep on repeating ad infinitum, right? Model 4, model 5, model 6, model 7, you are the boss here, you can choose 500 plays, right? Now, it can happen that the second model also fails to detect the pattern. The third model also has failed to detect the pattern, or it might do a very, very mediocre job of classifying. That's a different matter. Like this, we build a series of models. And once we build a series of models, we can build 100, 200, any number of models. Finally, you have now a set of models, not one. We have now a set of models. This set of models are applied by weighted voting procedure to combine the separate predictions into one overall. So finally, basically, we will combine all these things into one consolidated model. Right? This is a simple strategy that is used in boosting to improve your accuracy. Is there a guarantee that always it will work? It might work, it might not work. Nobody can give a guarantee. Right? So far it's clear, right? There's a simple way in which we are trying to improve the accuracy, right? Let's just take one example here. Let's start with this, right? A binary class problem, right? You have a few pluses, let's say it is class 1, and you have a few negatives here, which is basically the second class, correct? So the first decision tree does what? Basically, it just puts a line here and it tries to classify, correct? These two pluses, it has been able to successfully classify, correct? But we're putting a line here, it is not able to classify this because here you have 3 pluses and you have 4 negatives. So there is some level of error here, right? Now, what the second model does is basically it comes up with a decision boundary. Not here, its main focus is not this portion. The portion that the second model, focuses on is the pink region because that is where you have misclassification. So what the second model does is basically it tries to basically put a line here, right? It has been able to capture some of the lines here, some of the negative points, right? Now I can build one more decision tree here, which puts a horizontal line here. Here, basically you can see you have 3 pluses and 3 negatives. Correct? This is doing a good job of learning the patterns from the top. So this is the decision tree, right? Finally, if I combine all the 3 models, I've got the first decision boundary, I've got the second decision boundary, I've got, let's say, the third decision boundary. By and large, you can see here all the pluses can still be separated from the negatives. By and large, right? It's a very simplistic situation, but this is how any boosting technique will be, right? This is sequential. Sequential means basically the second decision tree, it is in a way affected by the performance of the first decision tree. The third decision tree is affected by the performance of the first two. The fourth one is affected by the performance of the first three, so on and so forth. One after the other. Boosting works one after the other. So far we clear with boosting. Boosting tends to increase the accuracy, right? Now let's focus on the second set of models, which are called as bagging, right? Bagging, right? Now here, when you say bagging, this is a combination of two words, right? When do you use bagging? Accuracy is not a problem, let us say. I've got through boosting, usually you'll obtain highly accurate models. But the problem comes to know where? Generalizability. I'm not able to generalize too many variables and systems. That's when your bagging as a technique comes into picture, right? How do we address bagging? This is just a schematic representation you can see here. You have the actual data, correct? From this actual data, what you're going to do is basically you're going to take a sample. This is called as a bootstrap sample, right? First step in bagging is basically there are two bagging, right? The first letter is basically B, and then you have bagging, right? It's B plus aggregate. So it is the letter B here refers to bootstrap. Bootstrap. Bootstrap is nothing but a sampling technique. So we will be basically using the bootstrap method to generate samples. Correct? We will be generating bootstrap samples or replicates. So this is the first bootstrap sample that we have generated. This is the second, this is the third. You can have any number of samples obtained from the bootstrap. But this bootstrap sample, I will be feeding into my first model. This bootstrap sample, I'll be feeding into my second. And this bootstrap sample, I'll be feeding into the third one. So here I'm showing three, you can run 30, 40, 300. Right? This first model will have visibility towards only this sample. It does not have visibility towards the rest of the samples. This guy here has visibility towards only this. It does not have visibility towards the rest of the rest of the samples. And this one will have visibility only to this. It will not have visibility towards the rest of the samples. Once you feed this, it will spit out a prediction. Let us say it will say that the first person is a high risk customer. Second model say no, he's a low risk customer. Third model will say basically that he's a high risk customer. Right? So out of three models, basically two out of these three models basically are say high risk. So majority wins, and the overall classification will be that it is a high risk customer. Are you clear with this?
Is the models the same?
It will be the same.
For the.
It will be the same. Here it is same.
For the bootstrap 1, 2, 3, it will going to the same ones.
Okay.
Are the variables are divided like group together?
I'll tell you. I'll tell you. Because this is a very high level perspective that I gave here, right? Right. So there are a couple of interesting things here, right? Now, what was the main problem when I use bagging? What is the main challenge that I'm trying to address? The moment you have high dimensional data, that will lead to overfitting. Take it for granted, especially if the number of independent variables are in double digits, 10 plus. Usually you will have overfitting problem. Usually, as thumb rule, it will be how is this solving that problem, right? Now there are so many things that are happening under the hood. It's a bit difficult to explain, right? Okay. Let me just start with this. I'll just explain this. See, you have this original data like this, right? Let me just say original data. I've got my original data. Correct? And this is, let's say I've got 500 samples. Okay, I've got 500 samples. Right? Now, once I have this original data and I feel that I'm not getting accurate results in such things when I do a decision tree or neural network and such things, I'm still not confident with any of those methods. What I decide to do is come to boosting or backing, right? Boosting solves the problem of accuracy, but it does not solve the problem of overfitting, right? Now, my only hope is basically with respect to backing, correct? What we do is basically we pass it through a layer of bootstrapping. Okay.
So this slide is about the original data and how we are
Split it.
dividing into different subset and then finally.
Yes. Yes.
Okay.
Yes. Again, disturbed unnecessarily. Okay, guys, we are looking at bootstrapping, right? Now, what is this bootstrapping, guys? It is not really a sampling technique. We say it's a resampling technique. You're taking a sample of a sample, right? And the curious thing here is that when we have this original data, if this has a sample of 500, right? Let's say I take the subset, this will also have 500. Yes. If this has 500, this one will also have 500. Each of these subsets will have 500. Correct. So this is my first bootstrap replicator. If this is 500, I'm taking a sample of 500. I'm taking one more sample of 500, and this will go on wherein I'll be taking one more sample of 500. Right? How this is working is basically it works on the principle of simple random sampling with replacement. So I'll just say SRS with the replacement. What do I mean with the replacement? Let us say instead of 5, let us say, let me just give you the example of 5, right? Let's say I have got 5 cards here in the original data set, right? You have card 1, card 2, card 3, card 4, and card 5. Right, 500 will be too much, so I'm just taking 5 simple examples. Take a visiting card. Let's say I'm just writing 1 on the first card. Second card, I'm writing 2. Third one, 3. Fourth one is 4, and the fifth card, I'm writing 5, right? So I just shuffle it, I mix it up well, right? I go there and randomly pick up one card, right? So here I may get card 1. In the first selection, right? Card 1. You have to correlate it with the Excel sheet. The first record, let's say, has been selected. I go back and put this card 1 back. Why? Because it is with replacement, right? Again, I mix it. Again, I shuffle, right? Now I've got 5 cards back. So when I go and sort of take a sample in the second iteration, let's say I get 2. Second card is what I'm getting. I take this, I note this, go back, shuffle it. Again, make a selection. Let's say I get card 2 again. In the third draw, I'm again getting card 2. I go back, mix it up, shuffle it well, right? I may get card 1. C1, C2, C2, C1, right? Again, I go back, shuffle it well. I may get card 5. I've got 5 different entries. So this is at the roller, correct? Which is this set has left out what kind of cards? Which are the cards which are left out? So here 1 is selected, 2 is selected, 5 is selected, but 3 and 4 basically are left. This is called
Selecting the
out of band.
Maybe twice, one car twice or
That's what I'm writing. It can select twice or thrice or 100 times it can select.
same.
Same card because it is with replacement. Okay, right? Whichever is left, which is not in the bag, we are calling it as out of bag. This is a separate sample. So far we are clear. Now let us look at this, right? Here you may select card 5. You may select card 5. Third time again card 5 may come. Fourth time card 1 may come and card. Are these two the same? It's very different.
No, very different.
C5. I'm selecting 5, 1, 2, and here I'm selecting 5, 1, 2. I'm sorry, the same. So let me just change this. Let's say I select fourth one. I select card number 4. It can select anything. It's random. It's happening randomly. So it can select fourth card. So for this, what is the out of bag? What is the leftover sample? 3. Only 3. So this is the out of bag replicate. Right here, you may have a situation where, let's say you're selecting C5, 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 and C4. Right here, what is left over is what? You have card 1, which is left out, 2, and 3. This is your out of bag for that particular replicator. Correct? Are you able to get this? So in one data set, I don't have all the records. In one data set, basically, I don't have all the records. It's a case of simple random sampling with the replacement that is going on at the backend. And therefore, I'm obtaining distinct samples. Now, just given an example of 5. If you have 5,000 or 10,000 records, you can imagine as to how bootstrapping would work, right? You're taking a replicate, you're taking a sample of another sample. This is at one level it is happening. One more thing which is happening at the back end, which is usually not emphasized, is so far you're clear. Simple random sampling, how it is taking how it is making the selection and what is left over here. That is what I'm writing as out of bag. Out of bag. It is not a candidate which is selected. Correct. This is not the only thing which is working. Let us say you have IV1, IV2, independent variable 1, and you have independent variable 50 independent variables. At the first level, basically, we have sampling being done at the row level. At the second level, what is happening is basically you also have a sample of the variables being collected. It is not that this this data set will have all the independent variables. It may get only independent variable 1. It may get the 10th independent variable, and it may get the, I don't know, 19th independent variable. The number of variables will not be the same. Number of variables will not be the same, right? So if I have 50 variables here, so this is in a way its way of handling high dimensional data, because here this could be only gender, let's say credit card status, and your payment behavior. How are you paying? Correct? Your gender, basically your past credit history or whatever it is, and your credit rating. These are the 3 variables that it sees. So it does not have the visibility towards the rest of the 47 variables here. Now, when you're looking at this set, right, what you have is basically it may be getting independent variable 22, independent variable 50, and independent variable 19. Right? So you may get 19. Correct? Here it can be independent variable 21, independent variable 45, independent variable 37. It can get a different. I don't have so much of control. Once I push the data and do bootstrap, all these things are happening at the backend. It is random. It is absolutely random. So what we are doing is basically we are shaking up the data set, and we are creating different flavors of the data set. Right? In YouTube, there's a wonderful video of a person called as Trevor Hasty and Tip Shirani. Trevor Hasty and Tip Shirani. They are the persons who are the brains behind these techniques, right? The second generation modeling techniques. Is this clear as to how it is happening, right? So you have IV1, IV10, whatever it is. In R, this random sample, right? Now you can technically ask me, sir, why should we build a model with 3 variables? Why not with 4 variables? 4 variables can be allocated or 6 variables can also be allocated. What is the optimal number? I don't know. Nobody can give you a number. Nobody can give you a silver bullet there. So this procedure of taking a random sample of the variables, that method is called as M-try method in your R studio. In R, in general, you get this in R. You don't get this in your Python and such things. It is called as M-try, the letter M and try, right? We have to just do a bit of exploratory data analysis and ask R to run different iterations and tell me what is the ideal number of sample of variables that I need to collect, right? When it comes to the rows, I've got the same set of rows, same set of samples. And when it comes to the columns, it is very, very different. This you can use for image processing. This can be used for text mining, any of these things. This is just a strategy of modeling. Yeah. Now, once I've got this data, I take this data and feed it into my first decision tree. I take this and I sort of feed this into the first decision tree. Right. And then I take this data and feed this into the second decision tree. Now, this data does not have any variables which are very, very similar to this.
So question, out of that, earlier way how I learned, but how I learned is that first step we have the sampling, first level of sampling. And then when we train, that is if we train with that sampling, it's a bootstrap sampling, because those are the different type of samples that we are training. But when it comes to out of bag, there from the first sampling, we are splitting into training and testing. That is what the remaining, what we
You don't
use
need
for
to.
testing
No,
is
wait,
becomes out of
no,
bag.
you don't need to do it. I'll tell you it. Wait. So far, it's clear, guys. DT1, DT2, and the same thing with here DT3, DTN, right? Whatever, nth model, right? Now you can just see here, this decision tree will be built based on, let's say, gender, income level, and marital status. This will be built on, let's say, marital status. It could be built on your credit history. It could be built on some other variable, right? So the output of this and output of this will not be the same at all. It will not be the same at all, right? Right. Now, once I build this model, I will get some prediction. Right? I will get some prediction here. I will get the nth prediction, right? Which means basically, if you have 5, we have taken the example of 5 different records you would have predicted. 5 different records you would have predicted. 5 different records this model would have predicted. Out of 5, let us say 4 of them are saying that yes, the first gentleman, whether I'm looking at gender, income, or tenure, whether I'm looking at gender, marital status, and his beginning salary, or whether I'm looking at marital status, or whether he's a senior citizen living in a particular locality, 3 out of 4 times, these 3 models are saying that he is going to be a high risk, a high credit risk, or he's going to be a churner. 3 is greater than 2, so majority voting. 2 times it can be. Clear? Now, how do you evaluate the performance of this set of models? Now, to evaluate the performance of these models, what we do is the model is built on these records C1, C2, C1, and C5, correct? The model is built. When I'm applying the model, I'm going to apply it on out of bag. Out of bag. These are not selected during the model. So the performance of a model is evaluated on those records which it has not seen. You can call it as test if you want, right? So same thing with this as well. Its performance is gauged on this second set of records. That is basically here you have only card 3, whichever is left out. Basically that it will score and see, okay, these are the records which you have seen and you have predicted based on 3 variables, marital status, income and something else. Now tell me based on your learning, how will card 3 be? Now this guy, right, it could be tell your contract status and something else. You learned a pattern. Now based on this, you tell me for card 1, card 2 and card 3, what is the?
Right, that initially when it is made a bootstrap, is that be considered as a train data?
You can use any language here. You can use train, test, whatever it is. I'm calling this as a bootstrap replicate because this is the output produced by a bootstrap. If you can understand this as training,
Yeah,
you can use the same language. You can go with the same language. All right. So effectively, right, is this understood? Right. So out of bag, how is it behaving for the unseen cases? Correct. So here high dimensionality problem is addressed because in usually there is a formula for this as well, wherein if you have n variables, they say square root of n squares minus 1. You can just check it up. I'm forgetting the formula. Those many variables you should select this. Right. But in R, basically there is something called as a M trie. Once we run this exploratory data analysis, that comes back to me and says, boss, you can, it is best that you choose to take 2 samples, 2 variables to build a model at a time. So when this model itself is built with the 2 variables, not your original list of 50 variables, where it will not be a deep tree. It will not be a deep tree. It will be basically a shallow tree. Shallow tree is basically the enemy of overfitting. Deep tree is itself synonymous with overfitting. If the tree is very shallow, you will usually not get overfitting. If the tree is very, very deep, that will result in overfitting. So when I'm giving it merely 3 variables or 4 variables, which is a lot lesser than the original set, naturally the output of this will not have that overfitting problem to a large extent. After doing all the circus also, there could be some instances wherein there is a overfitting. We do not know. We have to check it. But by and large, when I'm running this 500 trees or 50 or 200, whatever the trees, overfitting problem to a large extent is taken care of.
So this is one of the strategies, right? Like we can use same features for all the trees, or maybe we can leave it as.
See, hold on. Let us say you're using same features. Let us say 50 features you're using. Correct? You can use it, but the high dimensionality problem might still not be taken care of.
Yeah.
That's the biggest problem, which means you're borrowing the old problem and you're putting it in this method, which is not what we want, right? We started off this argument by saying bagging techniques are designed to handle high dimensionality problem because high dimensionality results in overfitting. I want to eradicate. If I start using the same number of variables, 50 there, 50 here, 50 here, 50 here, 50 here, I am borrowing the same problem, putting it in this method. So that defeats the very purpose of bagging actually. So take a sample of variables, always advisable. Take a sample of variables, take a sample of the records as well, but the sample size will be the same. The variable size will be different. Out of bag is this OOB, out of bag. Just focus on the words out of bag. They are outside this bag, a separate sample on which the performance of this model has to be evaluated. Right, for a fresh set of cases which it has not seen at all. Since it has not seen at all, its challenge is even more, saying that boss, for the unseen cases, are you able to basically predict well or not, right? So one advantage here is that every record, by and large, I'm imagining, by and large, every record will participate in the training? By and large, there will not be one single record. If I'm taking 500 or 600 trees, by and large, every record or every block of records will get to participate in the training. So no record is left out. And therefore, no pattern by and large can go undetected.
Since we are using decision tree also, like as we said.
I have 3 people shooting it. 1, 2, 3. Please, yes.
No, as
I'll
I
just-
explained, like just setting up on the previous question, since it is a decision tree, naturally it changes the variables in each model. So it changes the features that is selecting to train the model. Right, in decision tree also, the number of features that it selects, it varies. Like with the formula, what you said.
See, if the variable selection you're saying.
Yeah.
If the criteria is the same, by and large, you may get the same variables coming up again and again, right?
But each.
If the criteria, let's say the Guinness coefficient itself, I'm going, let's say in C5.0, I'm using information gain or entropy.
Yeah.
For this data set, by and large, if the entropy for gender itself is lesser, consistently, that variable itself will keep coming up again and again. Because the formula will not change. What has changed? Nothing much has changed actually. Here and there, maybe for one decision tree, maybe let's say gender has not come up as the important variable. It might be the second important variable. So you're not correcting that problem adequately unless you're taking the sample here. If this decision tree does not get to see gender at all, with the remaining variables, it has to basically grow the tree and then make a prediction, then I can still trust it because the net aggregate, finally, when you aggregate the results, basically, there is so much of shaking of the data that you have done. You have taken a sample of the variables. You have also taken a sample of the records, and then you're giving it a very, very challenging task of evaluating the performance out of the bag, right? Then by and large, this would be what are called as robust techniques. To a large extent, robustness can be guaranteed by this, not by the ones which are seen.
So out of that sample test,
Yes.
after that, what it will do? So it will check particular first efficiency or first model has done. So
Yeah, it will basically check in each of these basically in each of these samples basically. You can see out of bag samples. Out of bag error rate is high in which of these decision trees. Let us say for the third model that we have built, the out of bag error is basically the least. We can go ahead and specify either we can go ahead and specify that particular model as the champion model, or what we can do is basically now we can just focus on the results of only this particular model. Since we are getting only these 3 or 4 as the most important variables, the rest of the variables I can remove and build one final model with only those 4 variables, which is giving me the least out of bag error rate.
so when we run that bootstrap
Replicates.
model,
Yes.
at the end we get the result. We're not seeing that internally how the out of bag.
We'll get the out of bag error here for the 5 samples. What is the out of bag? That we can make it display. It's a bit hard, slightly hard, but you can always use this out of bag, right? And within that out of bag also, if there is too much of fluctuation, that's again basically that the variables basically each set of variables are giving you very, very different results. So finally, what you can do is basically you can, let's say you run 50 different models, right? Compare the out of bag, sort it in ascending order. Whichever sample has generated the least out of bag error, freeze on that particular model and say that these are the 3 best variables, and I will go ahead and build my final model with these. You can do that if you want. I'm not looking lost. Okay.
No.
Right? This is what happens in bagging technique. Bootstrap aggregate, right? So this is the stage where we are doing. This is the most important stage, right? This is your stage 1, right? wherein we are doing bootstrap, right? And this is the stage. Eventually, when we'll have 10 predictions being made here, this we have to find a strategy of aggregating. You have to aggregate, right? So you have bootstrap, and then they've picked up this word. So that's how they've just combined these words and they're saying this as bagging techniques, right? The letter B and right. So here, if you are doing a classification kind of a problem, the majority class, the mode is used, right? Maximum mode of 50, 30 times a person is called as a defaulter, 30 will be called as a defaulter. On the other hand, if you're predicting a scale dependent variable, you're taking the average.
Will it give a matrix like that?
What matrix you are looking for?
Yes, or no?
It will just give you the final predicted class. That's it. So far, we are clear, guys. Okay, so this is what is happening. Majority voting, and right, this is what I was just explaining. Important features of random forest case. Right, 3 or 4 important, very important features is basically we are introducing a lot of diversity in the data. We're bringing in so much of diversity in the data. If I have to just give an example, cricketing example, right? Now, for a long time, if you've been watching cricket, Indian cricket team, they do very well in India, but outside India, on foreign pitches, they fail, right? Why? Because our batsmen do not do well against good fast bowlers, right? Your decision tree and such things are like that. They are designed, they can handle certain conditions under certain circumstances, certain conditions they do well. But a good batsman is what? He's somebody who can handle spin bowling, fast bowling, medium pace, left arm, everything. Your random forest is like this because we are bringing in so much of diversity in the variables. There is so much of diversity here. That's a very important point. Independent variable 1, 10, and 19. Very, very different from variable 22, 50, and 19. Here, one more set of variables. Here, one more set of variables. One more set of variables. There is so much of diversity that we are bringing with respect to variables, as well as with respect to samples here. This diversity, and when you have such a diverse collection of variables, and then you're feeding it in, obviously you can expect the output that is being produced after majority voting that can be relied upon more as compared to one decision tree model. One decision tree model, now that you think of whatever you've learned, that appears very, very silly and very simplistic, isn't it? You're just building one logistic regression. Right? So what I was just showing here, bagging, right? This entire school of thought comes under what is called as random forest. So all these things, whatever I'm saying, one classic example of bagging technique is what is called as a random forest. A forest has many trees, right? The same metaphor they have used. Instead of one, we are building multiple trees, right? So diversity is one thing. Second one is basically the curse of dimension, right? So having too few variables is a problem, but the curse of dimensionality is reduced to a large extent because a lot of variables, when you have, it results in the problem of overfitting. You can't avoid it. So we are basically addressing the problem of curse of dimensionality, right? Third one is basically, here we are talking about parallelization. Boosting was a sequential model, one after the other. Third model had a dependency on second, sorry. Fourth model had a dependency on 1, 2, 3. Fifth had a dependency on 1, 2, 3, 4. But this guy here is working parallel. This decision tree, basically, he sees second decision tree. He has a set of records. He has 3 variables. He's trying to build a model with only those 3 variables. That's it. He does not know about the remaining 47 variables. He does not know at a later stage my predictions will be collected. So parallelization is what we are looking at, right? I'm writing train test split, but here actually more than the train test split, you can do it. It's just another technique. We are more concerned about out of bag performance because those are the records which it has not seen how a random forest model behaves on OOB, out of bag replicates. That is the test of its performance. And these models are robust and more stable. They tend to be more stable than other models. Okay, just at a high level, basically, Why do you prefer random forest over decision tree? Normally suffers from the problem of overfitting. Decision tree models, highly accurate, very interpretable, easy to understand everything, right? But overfitting problem will be there. Decision trees normally suffer from the problem, so it's about to grow without any control. Okay, fine. It's comparatively slower. This guy is faster because it is running only one model. Here, if I have to operationalize 500 models, system will collapse. Correct? So see, because there are so many things which are going on here. If there are 7,000 records, 7,000 into 50, because 50 samples I have to take. Right? If it is 500, you can take 500 theoretically, but 7,000 into 500, those many samples you have to take. Right? Well, that is one. And secondly, you have a lot of variables here, right? It has to run 500 models. Just imagine how much of resource intensity is there in a random forest model. So all of your random forest model synthesis will be damn slower as compared to your traditional decision tree model. Okay. Randomly selects observations, builds a decision tree, and the average results are taken. It doesn't use any set of formula. Give me the formula. I can't give you any formula and such things here, right? Because it is developed from that. Okay, important hyperparameters. Okay. Enhance the performance and predictive power of the models. Why do we need hyperparameters? That's the thing, guys. Right? We can't manually search, right? Should I take a sample of 2 variables or 20 variables or 8, right? So we need a bit of help from the system itself to tell me what are the ideal number of parameters. I've told you one of the important hyperparameters is mtry in R. Mtry, okay? So to increase the predictive power, right? Hyperparameters have basically 2 functions. One is basically we have to enhance the performance and the predictive power of the models, and we want something which is very, very fast, right? I can't wait for ages for a random forest to for a solution to converge. So 2 things. One is basically performance driven, and second one is basically fast. Make it fast. When you're talking about predictive power, if you want to increase the predictive power, these are the 3 control points that you have basically. Number of estimators or number of trees. Don't try with 50 or 500. I mean, it can be done, but it is time consuming. Sometimes it keeps going, right? Try with something less. Number of trees you can control. This will have an effect on predictive power. Next is basically maximum features, the maximum number of features random forest considers while splitting a group. I told you, right? Taking a sample of 3, you can give it as 4, 5, 6. You can do it, right? But fewer the better, at least when you're beginning with, right? Lastly, minimum sample in the leaf determines the minimum number of leaves required to split it, right? So these 3 things will have an effect on predictive power. Sir, I'm okay with predictive power, sir. I am interested in speed. I want to control the speed of random forest. Then these things, n_jobs. How many processors it is allowed to use? Usually this is put from the point of view of H2. You might have used H2 at some stage, correct? So there again, you have gradient boosting. So here, there you have n_jobs, correct? If you want to expedite the process and such things, focus on this. By default, n_jobs, if its value is set to 1, correct? It can use only one processor, but if the value is -1, there is no. It will just choose the number of processors at the back end to process so many decision trees automatically. If you use 1, default will be 1. If you put it as -1, any number of processors can be used in H2 and such things. Second control point that you have is basically a random state. Controls the randomness of the sample. The model will always produce the same result if it has definite value. It's like your set.c. Last one is basically your OOB score, out of bag score. OOB means basically out of the bag. It is a random forest cross validation method. So this OOB specifically you will get for random forest. Out of bag, you'll specifically you'll be getting this for random forest only. In this, 1/3 of the sample is not used to train the data. Instead, used to evaluate its performance. As a general thumb rule, under the OOB score, 1/3, 33%, right? Out of 100 records, 33% is not what your first decision tree see. It is able to see 67% of the records, correct? Of its performance. These samples are called as out-of-band samples. I've already explained this. Clear guys, hyperparameter tuning. One controls the predictive power, one set of hyperparameters, the first three parameters which I've showed. These are the ones which are used to control the predictive power. And these guys, these are the three things which are used to control the pace or the speed of the model. So for clear, Bhavna? Okay, if for any of these things it can be used, guys, right? For any of these models, it can be used. Just it can be there are a lot of text, but it can be used for both classification as well as regression related problems. Guys, that can be done. Overfitting, definitely it performs well even if the data contains null and missing values. Case there's one more advantage here, so less data cleaning is required, right? Otherwise you have to manually clean and all. Here we can just overlook upon this. Each decision tree creates an independent is created independent of the other. Thus it shows the property of parallelization. Very, very important. The property of parallelization here in boosting it is sequential models. Okay. Diversity is very important. It's immune to the curse of dimensionality. All right. So this is how it is able to handle this problem. Okay. I think disadvantages. These are the only two things, and it is less interpretable as compared to decision tree. There you will get a decision tree, right? One controlled, one beautiful decision tree which you can show. But here, since you are running 60, 70, I can't show 60 decision trees. I can't show, right? What you will get basically is the key drivers. What are the important variables? And finally, is the score you will get. That's it. Nothing else you'll get. Right, it will just aggregate and finally in just one piece, one line of code. So for one line of code, you did give so much of explanation, so much of things are happening at the back end. I can't show you any of these things at the front end, right? Should we break for coffee and come back and start this? Right? Okay. Shall we break for coffee, guys? We'll just take 15 minutes break. We'll just be back by around 11:50. We can get started.